Well, the next system is the second order oscillatory system. Transfer function with complex conjugate poles if zeta, here the damping ratio, is between 0 and 1. This is a system that you have encountered in the course of my colleague David Rouchard, Fundamentals of Control Theory, right? Omega n is the natural frequency, right? And the damped natural frequency is defined as follows. You can rewrite this transfer function as follows, and what is done over here is really to construct a sum of squares using these two first terms. So s plus zeta omega n squared, you'll have s squared plus 2 zeta omega n s, and then what you'll have too much is zeta square omega n square, and you'll have to kind of subtract it, right? So this transfer function, you can rewrite it like this, and as you can see, this is the Laplace transform of a damped sinusoid, right? Here we are using the translation in or the shifting in frequency, and in the inverse Laplace transform you'll have a term involving the exponential of minus sigma theta. But what you can see here is that you have poles in minus sigma. Sigma here is zeta omega n plus minus the damped frequency. So if we compute the inverse Laplace transform, this is what you obtain: a impulse response that is, well, to have a sign you would need here at the numerator omega d. You don't have it, so you'll have a gain here omega n over omega d, right? Then you'll have this exponential of minus sigma t. This comes from this translation in the s domain by sigma, right? And then a sine of omega d t times u of t. Okay, so such a system has an oscillatory behavior, and the impulse response is a sine that is damped, and a system that has such a behavior is, for instance, a spring mass system with friction. In the previous slide we had considered a zeta between 0 and 1. If zeta is larger than 1, the system is overdamped, and we have different real poles. These are these real poles, and then you can see this type of system as the succession of different first order systems in series, and we have considered that type of system before. If zeta is equal to 1, then the system is critically damped, and we have a double real pole. So we have P of s is equal to omega n squared over s plus omega n squared, and if you take the inverse Laplace transform, this yields a, well, impulse response that is omega n squared t exponential of minus omega n t, right? So we have this special mode here because of the double real pole. We had already computed the impulse response of this second order oscillatory system, right? And we had rewritten the transfer function as follows, and you can see here that the impulse response is a sine at the frequency omega d, so the damped frequency that is damped by this exponential. And to find this, as I've said before, you need to use this property of translation in frequency, or this frequency shifting property, and here it is. So here you can see the impulse response of that type of system. The natural frequency is 1, right? Remember that the natural frequency is 2 pi over the natural period, right? So you can see it in for the undamped system that the period would be 2 pi over here, and you can kind of see indeed that when the zeta is decreasing, so when the damping is decreasing, well, you can see here that this sign takes more and more time to converge to 0, and you can see that when zeta is decreasing, you can start to recognize this natural undamped period. You can of course also obtain the step response of this second order oscillatory system. Well, you have to take the transfer function and multiply by 1 over s. This is what you obtain, right? And to compute the inverse Laplace transform, you need to perform a partial fraction expansion, and this is what you obtain. What you can see here in this term is the Laplace transform of a cosine that has been frequency shifted, right? And this is the Laplace transform of a sine that has been frequency shifted. So here is the time domain response, and as we had anticipated, you can clearly see here the cosine at the damped frequency that is damped by this exponential of minus sigma t, right? And you have a second term with a sine at this same damped frequency and also damped by this same exponential. So you'll have something that will be creating this envelope, right? This is this one over here, and then you'll have this oscillation in this envelope, right? This is something that you have studied in the course of fundamentals of control theory, and sigma here is really zeta omega n, so that's related to the real part of the poles of the transfer function, and omega d here is the damped frequency, so that's omega n times the square root of 1 minus zeta squared. So if zeta is becoming very small, then what you see here is approaching the natural frequency. So here is the associated step response for different values of the damping, and you can clearly see that this oscillation is damped by this exponential of minus sigma t. Sigma is zeta omega n, so you can see that when zeta is increasing, right, the damping is increasing as well. You should not be able to draw the step response of this type of system, but you should be able to recognize it. Notice also that when zeta is becoming small, you can recognize the natural frequency of the system and its associated period of 2 pi. Notice also that at the origin we have that the step response is 0 and the associated slope is also 0, and this is because the associated transfer function has a relative degree of 2. The degree of the denominator is 2 and the degree of the numerator is 0, and therefore if you look for the step response at what is happening at the origin, you will see that of course both the step response and its slope are 0, right? We had seen something similar for two successive first order systems, so a second order lag system. In process industry, very few processes are designed to behave like a second order oscillatory system. But the closed loop behavior, that is the process in closed loop with the controller, often a PID controller, will very often have this type of behavior. We will assume that what you see here is the closed loop step response. So the input here is a unit step on the set point, and the response given here in green is this unit step closed loop response. And usually with the controller, what will happen if you have done a good design, of course, is that PV will settle in such a way that PV corresponds to the set point, and since the set point here is a unit step, well, PV will settle to 1 over here, to a variation of 1. Well, very often the closed loop step response is used to characterize the performance of the controller, and the performance of this controller is characterized in terms of the rise time, the settling time, and the overshoot. Well, the rise time is defined as the time that is needed for PV to go from 10% of its steady state value to 90% of its steady state value. The settling time is the time that is needed for PV to settle in a band of plus minus 1% around the steady state value of PV. The overshoot is shown over here. It's the peak value of PV minus the steady state value, right? And very often this overshoot is expressed in percent, and we speak of percentage overshoot. So the overshoot is expressed as a percentage of the steady state value. Well, we can now have a look at the frequency behavior, and for that we use the transfer function, and we divide numerator and denominator by omega n squared, and this is what you obtain. So we can then use the usual trick. We consider small frequencies here, small with respect to the natural frequency. We replace s by j omega, and if you do this here at the denominator, the dominating term will be 1. So we'll have that the transfer function evaluated on the j omega axis is more or less 1. So this means that an input sinusoid will produce a very similar output signal, right? So the amplification is approximately 1 and the phase shift approximately 0 degrees. At high frequencies, much larger than the natural frequency, well, it is this term that will be dominating. Okay, if s is equal to j omega, well, then s square is equal to minus omega square. So if this term here in the denominator is dominating, we can see that the transfer function evaluated on the j omega axis will be approximately minus the natural frequency squared divided by omega square. So there will be a decrease here in 1 of omega square, right? And there is a minus sign, so the phase shift at the high frequencies will tend to minus 180 degrees. This is a real number. The minus here will produce this minus 180 degrees, and this decrease in 1 over omega square will produce this slope of minus 40 dBs per decade. Well, we can now have a look at what happens at the natural frequency. So s will be equal to j omega n, right? And s square will be equal to minus the natural frequency squared, right? So at the natural frequency, this one will be minus 1. It will cancel out with this one, and well, the transfer function evaluated at the natural frequency is given by this expression that you can rewrite as follows. So we will see here that a sinusoidal signal at this natural frequency will be amplified by this factor 1 over 2 zeta. So a small damping factor will result in a high amplification, right? But whatever the zeta, you can see that the phase shift is minus 90 degrees. And this is indeed what we see. You can see here that at the low frequencies the gain is 1, so 0 dB, and the phase shift approximately 0 degrees. At the high frequencies, so high with respect to the natural frequency here, that is 10 radians per second, well, at the high frequencies we have a phase shift that is tending to minus 180 degrees, right? And well, the gain is decreasing here with a slope of minus 40 dBs per decade. At the natural frequency, so at 10 radians per second, you can see that the phase shift is indeed minus 90 degrees, and this holds for every zeta. But you can see that for a decreasing zeta here, well, you have an higher and higher amplification at this natural frequency. For your information only, it is possible using an experimental closed loop response to determine the process parameters that are associated to the second order oscillatory system. For that you need the decay ratio, right? This is the ratio of the overshoot of two successive peaks, so d3 over d1. This allows you to obtain the damping ratio zeta using this formula, and then by measuring the peak time, so this is the time from the start of the step to the first peak value, right? Well, you can use this peak value to compute the natural frequency as you have just obtained using this formula here, the damping factor. A second order oscillatory system can be implemented using two integrator blocks as follows, and if the damping ratio zeta is 0, well, you obtain the following implementation for a system with two poles on the imaginary axis. This is a system that implements an undamped behavior. The impulse response of the system is a sine, right? And the step response will have an overshoot of 100%. Well, in itself, this might not be very interesting, but keep this in mind later on when we'll consider the PI control of an integrating process. So here, the integrating process will be this 1 over S, and the PI controller will be this part over here. Of course, in reality, there is also a proportional part that is adding, right? So you would have something like this added, right? This would then be the proportional part, this the integral part, right? But if the integral part is dominating, you can see that you have this kind of closed loop system, and that you will have, well, an undamped behavior. Okay, so beware of PI control with dominating integral action, as it will cause oscillations on an integrating process. Let us do a little quiz. So you have to identify the step response of a second order lead lag. So 2 lag time constant and 1 lead time constant, and T lead is larger than T lag 1 and T lag 2. So I will show you the different possibilities, and at the end, well, you can push the pause button, use the rewind functions, and you have to try to identify the correct response. So push the pause button and use the reverse rewind functionalities to identify the correct response. We have here a system with a relative degree 1 as the denominator as degree 2, 2 lag time constants, and the numerator as degree 1. There is 1 lead time constant, and therefore using the initial value theorem you can see that this process has a step response that is 0 at the origin and a slope that is non-zero at the origin, and this is certainly consistent with A, right? It's also consistent with B, but here we have this damped oscillation, so we can exclude B. In C here we can exclude this response because we can see that there is a direct feed-through. The step response at the origin is non-zero. This corresponds to a lead-lag system, so 1 lead, 1 lag time constant. Here we can see that the slope at the origin here is 0, so this corresponds to a response of a second order lag system. And here again we can see that there is this damped oscillation, so we can exclude E as well. So we can see that the only response that is consistent with what is asked is response A. So the correct answer is A. Well, to give a word of explanation, we can see this second order lead lag system as a lead lag system. The lead S plus 1 over T lag 1S plus 1, followed by a first order system with transfer function T lag 2S 1 over T lag 2S plus 1, right? So this is a first order system. This is here a lead lag system. And here we have the output, right? And we can kind of imagine the output of the lead lag system, and we'll show it here in dashed. It would look something like that. It has a direct feed-through term, and it would look like something like that. And if this is the input now of a first order system, you can see that you will obtain this response. And as I've said, this is also consistent with this type of transfer function, because the step response must have at the origin a value of 0, which is the case, and the slope must be non-zero, and this is also the case. Let's do another quiz now in the frequency domain. So you have to identify the Bode diagram of a first order lead lag system. So 1 lead time constant and 1 lag time constant. So this is really a lead lag. The gain of the system is 10. The lead time constant is 1 and the lag time constant is 10 seconds. So I will show the different candidates, and then you can use the pause and rewind functions to find your answer. Well, using the parameters, we can see here that the low frequency gain, the static gain, is 10. So at the low frequencies we should have a gain of 20 dBs. The high frequency gain is non-zero here because we have a system with relative degree 0. There is a direct feed-through term, and this high frequency gain is Kp T lead over T lag, so it's 1, so 0 dB. We can see here that the lag action will start at 1 over T lag, so 0.1 radians per second, and the lead action will start at 1 over T lead. This is at 1 radian per second. We can exclude candidate A because the low frequency gain is not 20 dB. We have here Kp is equal to 10, so we should have 20 dBs. This is not the case. We have 20 dBs at the low frequencies for B, but the high frequency gain tends to 0, right? This is here a transfer function with a relative degree 1. You can see here that the phase will go to minus 90, right? And there is a drop here in the gain with a slope of minus 20 dB per decade. So we can exclude B. C seems to be consistent. We have here a low frequency gain of 20 dB. The high frequency gain is 0 dB, and the lag action is starting at 0.1 radians per second, and the lead action is starting at 1 radian per second. So this seems to be correct. Again, we can exclude this one here. At the high frequencies, the gain is tending to 0, and here again we have a problem, because at the high frequencies here we have a gain that is minus 20 dB, and we expect 0 dB. So we can see that the correct answer is C. Well, the next subsection considers non-linearities in the process, and we have seen in these surveys that we've seen earlier in the course that one of the non-linearities that occurs very frequently on a control loop is stiction. This means static friction, and this is something that is happening in a control valve. So you have a process, right? And in front of the process you have a valve, and this process is being controlled using a PI controller. It might be derivative action, but in most cases not. And we have the set point over here, and of course the feedback part, plus and minus, right? And what happens is that there is static friction in the valve, so that the output of the controller does not necessarily correspond to the valve real opening, right? Because of this static friction. Here we have a simulation of a closed loop step response. Same process, same PI parameters, and in, well, dark lines here we have stiction present in the valve, and as you can see, well, the results are quite different, and you can see here that the output of the controller in full line does not necessarily correspond anymore to the actual valve position that is shown here in dotted line. What we will do to explain this phenomenon is look at the steady state situation. So what you see here is the steady state situation, and we are only showing here the simulation in the case that there is stiction, right? So we'll assume that we start from here, right? And you can see that in this region PV is below the set point, so the error is positive, right? And because this controller has integral action, you can see that the output of the controller is increasing, right? But because of the stiction, well, the control valve does not open, and more potential energy is created, and at some stage then finally the control valve does indeed open, but of course it opens too much. You can kind of see that to have PV on set point you would have to use this average value of MV, and what happens here is that because of this accumulated potential energy the valve opens too much, right? And what happens is that now well, PV goes above the set point, and we have now a negative error, and the whole thing can start again. As you can see here, what is typical of Stiction is that MV evolves as a sawtooth type signal, un signal en dents de scie. To detect Stiction, what is usually done is to take episodes where a steady state is detected, right? And MV is plotted against PV in a so-called scatter plot. So you will see this kind of behavior that is typical for Stiction. What can be done to kind of see how severe the Stiction is to compute this area, and this will allow you to obtain an indicator that will tell you how severe the Stiction is in your control loop. This type of behavior is of course simulated, but you will have a very similar behavior on an actual process with Stiction. Stiction stands for static friction, right? And the problem is that the friction must first be overcome to initiate a valve movement. We have seen that, well, the output of the valve, and therefore the process input, is not changing continuously but in steps, and the size of the steps and their frequency depend on the amount of Stiction, but also on the loop gain, so more in particular on the controller gain, and this results in continuous cycling on PV. You can recognize the Stiction quite easily by looking at MV, right? You will see that MV will be evolving as a sawtooth type signal. The obvious solution is of course to repair the control valve. If this is not possible, it might prove to be useful to add a dither signal. This is kind of a noisy signal on top of the output of the controller, but beware of additional valve wear. Another solution that is sometimes advocated is to use a proportional controller. So a P controller without integral action, because it is this integral action that is causing this sawtooth behavior on MV. In order to obtain a small error on the control, SP minus PV, with a proportional control, you'll have to work with an MV bias, and this will be introduced in section 5. The next nonlinearity that is encountered very often is the saturation effect. The idea is that above a certain input, the output is not reacting at all or hardly reacting. What you see in magenta is a typical saturation. You can see here that the slope is changing all the time, and in blue you see kind of the idealized saturation, and here you can see that there is a region where the output is reacting linearly to the input. The most common saturation nonlinearity that you might encounter in process industry is of course the valve, right? And you know that the saturation limits are 0 and 100%, but a lot of actuators and processes will display some kind of saturation. It is important to know these saturation limits. For instance, when you're tuning a PID controller, depending on your working point, you might encounter or hit the saturation or not when you're doing a closed loop step response. Also, if not properly tackled, saturation can lead to integrator wind up, and we'll see this later on in the course in the section devoted to integrator wind up. Dead band or dead zones are common in hydraulic valves. The spool blocks the valve opening over here, with some overlap, so that for a range of spool positions, right, there is no fluid flow. Okay, so at the input of the process you have this deadband or dead zone nonlinearity. When you start pushing for some time, well, there is no opening, and then suddenly the opening comes over here, right? So usually in this type of deadband, well, dl and dr are the same, and the slope are the same as well. In this case the slopes would be 1, but this is modeling a, well, general deadband nonlinearity. So you can see here that if you push in the beginning you have no effect, and then of course the opening comes, and due to the pressure source, well, the piston will start to move. So here the deadband is at the input of the process. The dynamics that you find after the deadband, the dead zone here, are the dynamics from input x here to output y. So this is the movement, right? So it can easily be obtained using Newton's second law. We'll have m, so mass times acceleration, my double dot, is equal to, well, the driving force, and the driving force will be of course proportional to the opening, and let us say that it is k times the opening, so that's the driving force, and there will be of course a, well, friction force, c here will be the friction coefficient, times y dot, right? If we go to the Laplace domain, we have m s square y of s is equal to k x of s minus c s y of s. So the dynamics and the transfer function is really given by this transfer function over here. This transfer function is of course given for your information. It has nothing to do of course with the concept of a deadband. Here we illustrate that the dynamics from spool position to output is nonlinear, and that you have a nonlinearity at the input, which is precisely a deadband, and that's the concept we're illustrating. But after this input deadband we have a dynamics of this type over here. A deadband or dead zone is an interval of the input signal where the output is not reacting, so we're saying that the system is dead in this input interval. It is typically a nonlinearity that you'll find at the input, and some processes will exhibit this input deadband nonlinearity. Well, an example is the hydraulic system that we've seen just before. A deadband is sometimes used in PID controllers, and the idea is that it will allow to prevent actuator wear in the presence of noisy signals, right? So what we have here is the PID controller. As you know, the PID controller is acting on the control error, right, to produce the manipulated value. So what will be done is to put a block here at the input, right, and this will be this input dead zone, right? So at the input here we'll have the error, so this signal at the output will be the error after the dead zone. As you can see, the deadband is holding the control error if this control error is small in absolute value. So for instance, if this control error is so small that it is just due to noise, right, then what will go through the dead zone is a 0, and then when there is a change in error, right, that goes above the noise level, well, then the error will leave the deadband and the PID controller will see the error. We'll come back to that later when we'll talk about the PID controller. Well, the input deadband is very easy to implement using these equations, and these are given for your information, of course. If you're inside the deadband, then of course the output is 0, and when you're leaving the deadband, well, you have to start from 0, right? If you put V of t is equal to dr, so this is the end of the dead zone to the right, you have an output of 0, and if you go further, well, this has to be with a slope to the right of SR, hence this implementation of the output, and you have something very similar, of course, to the left of the dead zone. For a PID controller with input deadband, well, what is done is that the slope to the left and to the right is set to 1 in order not to interfere with the gain of the controller, and usually there is one deadband parameter, which is D here, which is half of the width of the deadband. Backlash typically occurs in transmission systems, and the backlash is caused by the small gaps that typically exist in those transmission systems. So in this representation here, the input is the input to the backlash, and this is the output, but the input is of course coming from the controller, right? So it is MV. And as you can see over here, if the controller output is going in the same direction, then it is not a problem. The output of the backlash here in magenta will typically follow, right? But assume now that you have a reversal of control. Okay, the control is going into the other direction. What happens is that the actuator output will not move. You can see that the output is constant until the backlash is taken up, and it's only when the backlash is taken up that the output will start to go in the other direction. It will be, of course, important to minimize the effect of backlash so that its influence on closed loop performance is as small as possible. We have seen that this control reversal causes, well, a problem because it takes some time for the backlash to be taken up, and this is really a dead time, an apparent dead time at control reversal only. So this will have a kind of destabilizing effect, and this effect will manifest itself as continuous cycling. In the previous examples, we have considered static nonlinearities. Of course, there are also nonlinearities in the dynamics, and they will manifest themselves in very different behavior around different working points. We will illustrate this using a simple pendulum system, and this system has the advantage of showing that the behavior can indeed be very different around different working points. Notice that container cranes or grab cranes will have very similar dynamics, and there the working point depends on the sway angle theta, but also on the pendulum length. For a container crane, for instance, well, the length of the pendulum will be changing continuously, and this will also have an impact on the dynamics, on the resonance frequency, for instance. Note that in this very simple example, we will assume that the length of the pendulum is fixed. We can very easily obtain the dynamic equation for the pendulum using Newton's law. right? So mass times acceleration, the acceleration will be L theta double dot. So this is mass times acceleration, and then sum of the forces. You'll have the force due to gravitation here, minus mg sine theta, and you'll have a friction force that will be proportional to the velocity, and the velocity is L theta dot. If you use a friction coefficient c, then we have minus cl theta dot, and this is the dynamic equation that describes the pendulum movement. Remember that the dynamics are ml theta double dot, mass times acceleration, is sum of the forces, so mg sine theta minus cl theta dot. As you can see here, the dynamics are non-linear, and this is of course because of this sine theta in the differential equation. So what we'll do is look at this differential equation in the neighborhood of theta is equal to theta 0. So this will be our working point, and we'll look at small variations around this working point. If we take derivatives, we have theta dot is equal to d theta dot, and theta double dot is equal to d theta double dot, right? You know that sine of x, right, in the neighborhood of a is, well, the sine of x evaluated at x is equal to a plus the derivative, which is a cosine, right, evaluated at x is equal to a times x minus a, right? And this is coming from the Taylor series. So what we can do over here is look at the sine of theta in the neighborhood of theta 0. So this will be sine of theta 0, right? This is sine theta evaluated in theta is equal to 0 plus the derivative. It's a cosine, right? So cosine evaluated in theta 0 times theta minus theta 0. So this is d theta, right? So if theta 0, because we will be linearizing around theta is equal to 0 and theta is equal to p. So if theta 0 is equal to 0 over here, we'll have sine theta is approximately, this is going to produce a 0, the cosine of 0 is 1, so this is approximately d theta, right? So if we inject this in this nonlinear differential equation, right, and we replace sine theta by d theta, theta dot by d theta dot, and theta double dot by d theta dot, you have the linear differential equation that describes the variation d theta around this working point. If you take theta 0 is equal to pi, right, we'll have sine theta. This will still be 0. Now cosine of pi is minus 1. We'll have sine theta is equal to minus d theta, right? So we end up with this differential equation, and this will describe the behavior of the pendulum in upright position around theta is equal to pi, and d theta now is of course the variation around the working point pi. If you take those two linear differential equations and you go to the Laplace domain and you write the transfer function, you will see that in this case at the denominator you will have s squared, right, plus c over ms plus G over L, right? And here you'll have something similar, but with a change of a sign over here, right? And well, if there is no friction, you can kind of see that you'll have two poles here that are complex conjugate on the imaginary axis. If C is different from 0, well, you'll have two stable complex conjugate poles, so you'll have this oscillatory behavior. In this case, if C is equal to 0, you have two poles, the square root of G over L and minus the square root of G over L. So you can see here that you have two real poles, and one of these poles will be unstable. So you can see in this case that depending on where you linearize the system, you have a very different behavior. Around theta is equal to 0, logically you have a stable behavior. If you linearize the pendulum in the upright position, well, it's kind of obvious that you'll have a very different unstable behavior around that working point. The focus of the course lies on linear control techniques. So if the system is strongly nonlinear, the designed linear controller will at best work around one working point. So what we will see later on in the course, and this is in chapter or section 6, that you can really adapt the controller, and one adaptation is to adapt, for instance, the gain of the PID controller. This is called gain scheduling. Another adaptation is to do controller scheduling and let all the parameters, in most cases it's then the gain of the controller and the integral time constant, evolve with the working point. This kind of technique can also be used with internal model control. So you let the gain of the process, and because the tuning parameters then become the process parameters, you let the gain of the process and the time constant and the dead time evolve with the working point. This will be viewed in section 6. If the nonlinearity is static, what you can do is invert the static nonlinearity, and one way to do this is to use the control valve characteristic to compensate this static nonlinearity. This is explored in the next slide that I will leave for your information. One technique that is also left for your information is so-called linearizing or feedback linearization control. The idea is to use a controller, a nonlinear controller, to transform the nonlinear system in an equivalent linear system. Once you have this equivalent linear system, you can use standard linear techniques to design a controller on top of the linearizing controller. As you have noticed, I have skipped the subsection on modeling. It is there for your information. This subsection deals with first principle modeling, so modeling using the equations of physics, and data-driven modeling. The students in control engineering have separate courses on those topics. If interested, you can have a look at the slides or follow the associated courses that are available online. Very often, to design an internal model controller, a predictive PID, a Smith predictor, or to obtain a feed-forward law, we are satisfied with a good enough approximation of the process, and often this approximation involves a Broida model. A Broida model is a simple model with one time constant, a static gain of course, and a delay in the system, right? So there are essentially two ways to arrive at this type of model. The first method is to obtain an open loop step response of the system, so you'll have to experiment on the system, and then you can obtain the gain, the time constant, and the dead time using graphical methods. And this is what you have done in the control lab that is associated to the course Fundamentals of Control Theory. Another approach that might look unfamiliar is to use first principle modeling. So this is using the equations of physics to obtain a model of the system. Usually this model will be complex in the sense that you'll obtain a transfer function with a high degree denominator, right? So this transfer function will be too complex for the methods that are used in this course, and the idea is that you can obtain a simpler model using model reduction, and this will be investigated in this subsection. Note that we use the notations t bar and theta bar because they are the best estimates of the time constant and the delay for this approximation of the process using the Broida model. In this slide we present another graphical approximation method that can be used to estimate the parameters for a first order system with delay, so a Broida model, right? So here we have obtained, using experimentation, a unit step response, in open loop, and this graphical approximation method, you'll be able to use it to identify an approximate model for lag time processes, okay, where you have a succession of several first order systems with also possibly a dead time. The gain Kp can be simply read by considering the steady state behavior. So you take the delta PV and you divide by the delta MV. Here we have a unit step response, so the delta MV is 1, and you can simply read the static gain from the steady state value of PV, right? So we are of course interested in the equivalent delay and the equivalent time constant. For that we have to look for the inflection point, right? The inflection point is the change in curvature, and the point where you have a change in the sign of the second derivative, right? Here you are, the function or the response is concave upward, and from here on it's concave downward. So here you have the inflection point and you can draw the tangent. It is not always easy to draw this tangent, as there might be some noise on the experiment that you have done, right? But once you have drawn the tangent, you can look for the times at which the tangent meets the steady state response, right? And the time at which this tangent meets the original PV, and it is now possible to obtain an equivalent delay and an equivalent time constant as shown here on the screen. Once you have obtained Kp and the equivalent dead time and time constant using this graphical method, you can obtain the approximated step response, right? And it is shown here in a sign. You could even see how good a job that you've done by considering at a certain time here the error, okay? And the estimation or approximation error will be PV at that time, so what comes out of the experiment, minus the approximated PV at that same time. So you can kind of compute the approximation cost as 1 over n, and here is the number of data points that you have collected times the sum of the errors squared, right? And this leads to the idea that what you could do is, well, try to minimize such a cost, okay? And this leads to an optimization problem where you minimize an identification cost that looks like that over kp t bar theta bar, right? And this will try to kind of minimize the discrepancy between what comes out of the model and what comes out of the experiment, right? And you can implement such an optimization using, for instance, fmin search, a MATLAB function. And this is something that you have done in the laboratory associated to fundamentals of control theory. Well, we'll now look at this other possibility, so to use first principle model and to obtain, well, a complex transfer function that we would like to simplify. In order to do that, we'll have to use some approximations. I have already introduced the first order Padé approximation when I've talked about the all-pass filter in the section on lead lag systems, right? I've already used this approximation here that comes from the Taylor series of the exponential, right? So you can write the Taylor expansion and around 0, so it's exponential of x at x is equal to 0, plus then you have the derivative, but it's the same, exponential at x is equal to 0 times x minus 0. So we have that this is 1, okay, this is 1 again, so 1 plus x. If you apply this to a delay, this is the approximation that you get. Well, there is another Taylor series that you can use. It's the Taylor series of 1 over 1 plus x, again in the neighborhood of 0. So you take the function and you evaluate it at x is equal to 0. Then you have to take the derivative. The derivative will be minus 1 over 1 plus x squared, again evaluated in x is equal to 0 times x minus 0, right? We only take the two first terms, so this is approximately 1 minus x, right? So this means that 1 minus theta s can also be approximated as 1 over theta s plus 1. So this leads to a method where you can kind of approximate a lag, right? A lag time constant by a delay exponential of minus theta s. Of course, this is only valid for small theta, right? Because in these expansions we make the assumption that we work around, for instance, here the origin. Well, the procedure is to approximate a complex transfer function with many lead and lag time constant by a simplified approximation, for instance a Broida system. So you can use these two formula to approximate small time and lead time constants. When we say small, it's small with respect to the main time constant. This formula over here will be used to approximate small lag time constants, and this one over here will be used to approximate small lead time constants. As you can see, a negative lead time constant is transformed in a delay, right? But this will also work with positive lead time constants, the delay will be negative here, but this has to be incorporated in the global approximated model, and as long as the overall delay is positive, this will work as well. Well, Skogestad has proposed a variation on the approximation method proposed in the previous slide, and it's called the half rule approximation. The idea is that the largest neglected time constant is approximated by adding half of the value to the time delay and half of the value to the smallest retained time constant. The other neglected time constants are approximated using time delays. Let us apply this to a third order process, 3 lag time constants and 1 lead time constant. And the idea is to obtain an approximation that is a first order model with dead time. So we'll use the 2 Taylor series approximations, right? Exponential of minus theta s is approximately 1 minus theta s, and it's approximately 1 over 1 plus theta s. So here we have a lead system and here we have a lag system. So what we'll do is first tackle the lead time constant. You can use this formula over here to replace it by a delay, and we'll just keep the main time constant, right? And the other 2 time constants will be replaced by a delay using this formula over here, right? Well, if we combine the delays, what we'll have is a delay, combined delay of 3.6, and this is resulting in the following first order model with dead time. So the first order time constant here is 5, and we have a dead time or a delay of 3.6 seconds. Well, we consider here the same process and we want the same approximating system, and now we're going to use Skogestad's half rule approximation, right? So the idea is that the largest neglected lag time constant, which is this one, is approximated by adding half of the time constant to the largest remaining time constant, right? This is 5. So if you had half of 3 seconds to 5, you have now a time constant that is 6.5 seconds, and the remaining part, so this is 1.5 seconds, is put in a delay. The other neglected time constants are just replaced by delays. If you now combine, you have a delay of 2.1 seconds, and well, the time constant was 6.5. You can kind of see here that this approximation using a first order model with dead time will not be that good, because the largest neglected time constant here, 3 seconds, cannot be considered to be small with respect to the main time constant. Well, here you have the associated step responses. So in green here, the original third order system. This system has a relative degree of 2, so you can see here that in the step response, well, at the origin we have 0, and since we have a relative degree of 2, we also see that the slope at the origin is 0. Here we have approximated using a first order model with delay. So we have of course a delay, and then because of the first order system we have a slope as soon as, well, the output of the system starts to react. And indeed we can see that with the Skogestad half rule approximation we have a slightly better approximation. Let us now approximate the third order system using a second order system with dead time with this transfer function, and you recognize the van der Grinten system? Well, there are several ways that you can see that this will be an improvement. In the previous case, we had approximated this lag time constant, but it cannot be considered to be small with respect to the main time constant, so we should probably keep it, right? Whereas this, well, third lag time constant is indeed small with respect to the main time constant, right? There's another reason. This one has a relative degree 1, degree of the denominator 3, degree of the numerator 1, so relative degree 2, but this one has also a relative degree 2, so this means that the step response of the approximation will be 0 at the origin, but that its slope will also be 0 at the origin. So what we will do is we'll approximate this lag time constant and this lead time constant by a delay using the Taylor series approximation, right? If you do that and you add the two delays, or the effects of the two delays, you end up with a delay of 0.6 seconds. And as you can see, we have retained the two biggest time constants. Let us now use Skogestad's half rule approximation. We look for the largest approximated time constant. This is this one. We take the corresponding time constant, and for half of its value we put it in a delay. Here you've got it, and the remaining half is added to the smallest time constant that is retained. So this is 3 here, and this is why we have here a time constant of 325, right? So we have now kept the main time constant. The secondary time constant has been modified using this half rule approximation, and if you add the delays, you have a delay of 0.35. Well, let us look at the step responses associated to the original system in green and associated to the two approximations resulting from the Taylor series and from Skogestad's half rule approximation, and you will see that there is hardly a difference. It's difficult to distinguish, as we had anticipated here, because the time constants that are approximated are really small with respect to the main time constant, and we have in our approximating system a relative degree of 2, and this results in a slope that is 0 at the origin. Well, we can now have a look at the approximations and the original system in the Laplace domain. So we can look at the Bode diagram. The process is given in green. You can see that if you use a first order approximation, well, you have problems at the high frequencies, because here we have a slope of minus 20 dB per decade, but the system, since it has a relative degree of 2, will have at the high frequencies a slope of minus 40 dB per decade. We can see here that with the second order approximation, right, well, we do a better job at the high frequencies, because here also the slope is minus 40 dB per decade. As far as the phase is concerned, we always have a problem, because our original process does not have a delay, and of course in our approximations we have a delay appearing. So at the high frequencies the delay will go to minus infinity, but you can still see that with this second order approximation, right, these two, we do a better job in approximating the original system, and we have a slight preference for the second order system that had resulted from Skogestad's half rule approximation. It is very important to be able to approximate a process like this one by a process like this one, because in section 5 we'll talk about IMC tuning, right? This is a method for tuning PID controllers, and in this method you will go and look in a table and identify the process that you've got, and from the type of process and the underlying parameters you can obtain, well, the gain of the controller, the integral time constant, and the derivative time constant. In this table you will never find a process like this one because it's too complex, right? But you will find this second order system with that time. Okay, so once you have approximated this system by this one, you can obtain tuning parameters for the PID controllers, and these tuning parameters will be valid also for the original system. To illustrate this, this is the table that corresponds to IMC based PID tuning, and as you can see here, there is no line here that corresponds to a third order system, but you can see that there is a line that is devoted to a second order system with delay. It has a lead time constant, right? But if you use this formula here with tau 3 is equal to 0, then you really have here a van der Grinten structure. We will see later, of course, how you have to use this table and where it is coming from.